Natural gas supply chain optimization. HI has the support of its technological allies, General Algebraic Modeling System, GAMS, and IBM, producer of C-PLEX Optimization Studio. Both products are incorporated into HI's artificial intelligence solutions. Hypothalamus Artificial Intelligence, HI. Digital transformation powered by autonomous and intelligent algorithms in real time. Presents its solutions based on artificial intelligence for decision-making for optimization of natural gas networks. There are many applications of mathematical models of optimization of natural gas system networks. Basically, for all applications the same model is used, from different points of view, which entails adjustments in the mathematical modeling. Some of the applications are natural gas market simulation, natural gas market and system regulation, real-time optimization of natural gas pipelines, and optimization of natural gas systems. Oil and gas pipelines nominations and bilateral contracts. The Natural Gas Market Module, NGMM, is the component of the USA National Energy Modeling System, NEMS, that represents the North American natural gas transmission and distribution system, and market. The module is a quadratic program that maximizes consumer plus producer surplus minus transportation costs. The consumer surplus represents the amount of money saved by consumers, who would buy natural gas at a given price but are able to obtain it at a lower one. The producer surplus represents the added revenue of suppliers, who could sell natural gas at a lower price but are able to charge a higher one. Therefore, by maximizing this combined surplus, and subtracting transportation costs and subject to balance and capacity constraints, the model arrives at an equilibrium price for the market. The image presents the NGMM natural gas pipeline network. Purdue University's SUFG, State Utility Forecasting Group, has supported experts from the Indiana Utility Regulatory Commission, IURC, since late 2001, with the goal of examining the impact of new electricity generating facilities within the gas system. The model determines the mix of purchasing, transportation, and storage decisions of local distribution companies, LDCs, which minimize the sum of purchasing, transportation, and storage costs over a 60-month planning period, subject to the following constraints. Consumer demand at demand nodes must be met. The flow capacity of gas pipelines should not be exceeded. Storage capacity limits of storage sites should not be violated. The amount of gas transferred from one pipeline to another cannot exceed the capacity of the interconnection, and long-term purchases and dispatch contracts. The image presents the network topology of the gas modeling system. Oil and gas pipelines nominations and bilateral contracts. Real-time optimization of natural gas pipelines. Nowadays, natural gas is one of the primary energy resources employed in many sectors, and it can be regarded as a bridge fuel in the decarbonization process. The transport of natural gas relies on a complex infrastructure, which needs to be properly managed to minimize energy consumption and CO2 emissions. The performance maps of the gas turbine-driven compressors have been linearized using the convex hull approach. The model includes all the technical limitations of the gas turbine-driven compressors, and it can handle flow reversals on all pipes. Moreover, it is suitable for cyclic networks. The MILP model is applied to a case study with 4 compressor stations, each containing multiple gas turbine-driven compressors, and a cyclic network consisting of 29 pipes. In this case, the MILP model was used to optimize the 24 hours of unit commitment, with time resolution of 30 minutes, and sections of a maximum length of 200 kilometers. The continuous variables of the MILP are 18,816, the binary variables are 1,421, and the constraints are 43,429. The optimal unit commitment and load of the gas turbine-driven compressors, GTDC, is shown in the figure. The solution uses only one GTDC of station S1, 3 GTDCs of different sizes in stations S2 and S3, while station S4 is always in the bypass mode. The optimized solution features an objective function which is 7% lower than a preliminary solution found by fixing the commitment of the GTDCs S1 S3, optimizing only the loads. Optimization of natural gas networks based on stochastic optimization. This model provides a review on the most relevant research progress related to the steady-state operation optimization models of natural gas pipelines as well as corresponding solution methods based on stochastic optimization algorithms. The existing operation optimization models are mixed integer nonlinear programming, MINLP, MODISL, involving a non-convex feasible region and mixing of continuous, discrete, and integer optimization variables, which represents an extremely difficult problem, to be solved by use of traditional monolithic optimization algorithms. However, no reference is made to advanced methodologies using large-scale optimization methodologies. A schematic of a natural gas transmission system can be conceptualized based on three subsystems: gathering pipelines, transmission pipelines, and distribution pipelines. The images shows a gas pipeline network composed of a tree and a cyclic network. The real-time model can handle differentiated electricity costs by time of day, or by load block, using this way to take advantage of low rates, or low marginal costs, in periods of electricity low load. A gas pipeline is a pipeline that allows combustible gases, natural gas, liquefied petroleum gas, to be transported on a large scale and over a long distance. Pipelines planning and scheduling. The optimization model includes the following types of nodes: production fields, consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial, and residential, and ports and terminals that can receive and/or send LNG. It is associated with liquefaction and/or regasification plants. People interested in the case can watch the video. Oil pipeline real-time optimization. Estimation of the operation profile. People interested in the case can watch the video. Oil and gas state estimation, or Kalman filter, applied to oil and gas pipelines. This section is based on the article Kalman filters for leak diagnosis in pipelines, brief history and future research. Given the extent of a pipeline's territory, it is virtually impossible to accurately measure the main operational variables along the entire length of the pipeline. It is possible to install remote terminal units, RTUs, scattered along the pipeline, with distances ranging from a few meters to kilometers. Typical variables measured by an RTU are pressure, flow rate, temperature, and valve positions. This implies that we only have measurements with high precision at the measurement points, nodes, and for the rest of the pipeline it is necessary to estimate what is happening, based on the observed variables. This can be achieved by the physical model that mathematically explains, through differential equations, the flow of the products moving in the pipe. This is a typical case of application of the Kalman filter, KF. Given the nonlinear nature of the flow process in the pipeline, one of the most commonly used methodologies is the extended Kalman filter. System communication architecture generally implies that all reaches report to the signal concentration hub, and from there go to the control center of the SCADA system. The communication center can be a satellite or a monitoring system at the operator's offices. Mathematical modeling can be organized as follows. A real pipeline that has all the real sections, including the measuring stations installed, and a virtual pipeline that has all the sections, including the installed metering stations, and the virtual stations, where the operator wants to have measurements. Using the Kalman filter, or one of its extensions or variations, the value of state variables in virtual stations can be estimated. In this way, the profile of the operation is formed throughout the entire pipeline. Due to operating conditions, onshore and offshore pipelines are subject to environmental loads, wind, waves, currents, seafloor movements, and earthquakes, which can lead to undesirable vibrations, stress, fatigue issues, and the propagation of cracks. In particular, the latter problem is a major source of leaks along with aging pipes, installation failures, illegal extractions, and terrorist sabotage. For this reason, in order to avoid environmental disasters, The oil and gas sectors invest generous resources for the development of robust and reliable leak detection systems. The detection and localization of leaks in pipelines may be using approaches based on the Kalman filter, considering that there are important contributions that use the Kalman filter as the core of a computational pipeline monitoring system. According to the authors of the article, without being exhaustive, the paper gathers the results from different research groups such that these are presented in a unified fashion. For this reason, a classification of the current approaches based on the Kalman filter is proposed. Then, a brief history of the use of the Kalman filter for diagnosing leaks is described, by mentioning the most outstanding approaches. Below is a table, divided into 3 images, with the works consulted by the authors. Leak detection in pipelines. Case, Nor Peruano oil pipeline. The state-owned company Petróleos del Perú, Petroperú, is one of the companies of transporting crude oil in Peru, and for this it has the North Peruvian Oil Pipeline, ONP, operating since 1977. ONP crosses the jungle, mountains, and coast, and is divided into 3 sections, Section 1, Section 2, and the North Branch Pipeline. ONP has a length of 1,106 kilometers from the northern jungle to the Bay of Our terminal on the coast. ONP has a transport capacity of 200,000 barrels per day, and plans to increase this capacity to 500,000 barrels per day. Data from Petroperú in 2021. Artificial intelligence in oil and gas pipeline safety, using game theory. Attacker and defender models. Attacker and defender models. The core of an attacker-defender model is an optimization model of an infrastructure system whose objective represents the system's value or cost to the defender, our society, while it operates. For instance, the maximum throughput of a pipeline network could measure that system's value, while power generation costs, plus economic losses resulting from unmet demand, could measure the cost of operating an electric power grid. In this type of problem, the leader's decisions affect the follower problem, and followers' decisions affect the leader problem. Each player, leader and follower has their own goals, represented by their objective function. The image presents the AD model as a B-level problem according to Heinrich Freiherr von Stackelberg's theory. Defender-attacker-defender models. The solution of an attacker-defender model identifies the most critical set of assets for a system. The ability to identify such assets leads to some obvious heuristics, to approximate the solution to the optimal defense problem, to identify a near-optimal defense plan, given a limited defense budget. But how do we identify the truly optimal solutions? Case, the U.S. Strategic Petroleum Reserve. This section is based on the paper Defending Critical Infrastructure. In the aftermath of the oil crises, the United States established the SPR. President Ford set the U.S. Strategic Petroleum Reserve, SPR, into motion when he signed the Energy Policy and Conservation Act, EPCA, on December 22, 1975. The legislation declared it to be USA policy to establish a reserve of up to 1 billion barrels of petroleum. Critical infrastructure protection. Development of tools to anticipate, identify, and measure the risks to which a nation or region's critical infrastructure is exposed. This is to reduce the risks and consequences of an attack. B-level and tri-level optimization models to make critical infrastructure more resilient against terrorist attacks are used. Each model features an intelligent attacker, terrorists, and a defender, us, information transparency, and sequential actions by attacker and defender. 3 real examples are presented. The U.S. Strategic Petroleum Reserve, the U.S. Border Patrol at Yuma, Arizona, and an electrical transmission system. Each exercise gathers open-source data on a real-world infrastructure system, develops an appropriate B-level or tri-level model, and uses these to identify vulnerabilities in the system, or to plan an optimal defense. Only the first case is discussed in this presentation. The vulnerabilities of a space-sprawling supply chain are growing and riskier. Human intuition is incapable of optimally dealing with all the attacks that such infrastructure may suffer in physical space, or in cyberspace. Decision-making artificial intelligence provides the right tools to maximize the success of those who must defend society. People interested in the case can watch the video. Homeland Security. Defending oil and gas critical infrastructure. A games theory approach. Oil and gas pipelines nominations and bilateral contracts. The nominations are the agreements made by the carrier and dispatcher to transport oil, natural gas, and petroleum products, using pipelines. This process normally occurs within a long, or medium-term contract, between the transporter and the dispatcher. In turn, the contract of the dispatcher, who can be a distributor, or a large consumer, is backed by contracts with end customers, and this process determines the demand for transport services that must be attended by the transport system operating company. Short glossary. Nomination, a request for a sender's transport service. Nominated quantity, refers to the volume that the sender requests, to be transported from a point of receipt, and delivered to a certain point of delivery, for a period of nomination. This must be authorized by the carrier. Nomination period, this is the period for which the dispatcher submits its transport nomination request. Cycle, subperiods into which the nomination period is divided. For example, days, weeks, fortnights, etc. Period, represents the period to be nominated, month, week, day, or another period agreed between carrier and dispatcher. The image shows a oil and gas pipelines nomination example. Mathematical modeling. The nominations have several relationships with mathematical modeling, namely, short-term, determine the demand for transport services that the carrier has accepted and authorized, normally assumed as an input data that is not affected by the real-time or short-term model. Medium-term, tactical planning, depending on the agreements between carrier and dispatcher, the medium-term model, of the order of months, week, days, can adjust the nominal transport plan to optimize the economic benefits and to improve the technical conditions of the operations, and long-term, strategic planning, this modeling can be related to long-term contracts. They can be used to accept the contract, verifying the required transport capacity, and definition of the price, or the marginal costs associated with attending the long-term contract. At the end of the last decade of the last century, Oil Express, a global natural gas company that operated several natural gas producing fields in multiple countries, asked HI for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making regarding the exploitation of natural gas field and its impact on Oil Express finances. Oil Express, Natural Gas Field Exploitation Planning. In 1997. Analysis of the gas market for the electricity sector. The main study carried out with high power was the analysis of the national gas market for the electricity sector. This is due to no alternative markets for natural gas other than national electricity generation. Pressure from the electricity regulator to sign contracts by generators and producers of natural gas for the purchase and the transportation of natural gas to give firmness to the electricity sector. Oil Express fundamental hypothesis: if the gas market is not sustainable, it makes no sense to sign bilateral contracts with electricity generators and to invest in extracting the natural gas, and the optimal strategy is to wait for the right moment in the future. The analysis was carried out using take-or-pay contracts as a basis. The take-or-pay (TOP) is a contractual clause, requiring the buyer to take the delivery of a specific amount of goods or services from the seller or pay a fine if they do not. Thus, it protects the seller against potential losses if the buyer refuses to complete the purchase by a particular date. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. Fuel supply contracts directly affect dispatch. In general, a contract has the following components. A percentage of the maximum consumption is purchased in the take or pay mode. The surplus over the take or pay is purchased under the pay-as-you-go modality, and there is a rolling period to consume the take or pay part. Given the seasonality of prices in the electricity sector, the model included top with a rolling period, which gives flexibility to the buyer to accommodate their physical purchases. But it complicates the generator decision-making process. Electricity and natural gas integrated modeling. Regional Modeling System Electricity and Gas. Purdue University State Utility Forecasting Group, SUFG, has supported experts from the Indiana Utilities Regulatory Commission, IURC, since late 2001 to examine the impact of new power generation facilities within the natural gas system. The model developed by SUFG determines the mix of purchasing, transportation, and storage decisions of local distribution companies, LDCs, which minimize the sum of purchasing, transportation, and storage costs over a 60-month planning period. The Henry Hub is a natural gas pipeline distribution system in Erath, Louisiana, United States. The piping system is owned and managed by Sabine Pipeline LLC and its affiliates. The Henry Hub is part of the highly integrated transmission network in the United States. The Henry Hub connects 8 interstate and 3 intrastate pipelines. It also has a direct connection to the storage facilities, where the Salt Dome Cavern is located. These facilities allow for injection and extraction cycles every year. An average of 350,000 Henry Hub natural gas futures contracts are traded on the CME/NYMEX each day. The Henry price is used to calculate the location basis at all other natural gas trading points in North America and is therefore the reference price for tens of thousands of derivative instruments and other trading contracts. But the U.S. natural gas industry is changing rapidly. Henry started out as a supply market center, but a resurgence of demand for natural gas in and around Louisiana is transforming it into a demand market center. The video. Indiana Sistema de Modelado de Gas Natural. Present this case in detail. Success case, China National Petroleum Corporation. The paper Operations Research Enables Better Planning of Natural Gas presents the use of mathematical optimization models for pipeline planning. China's natural gas consumption has nearly doubled in the past 5 years. To better meet demand, the China National Petroleum Corporation, CNPC, China's largest producer and supplier of oil and natural gas, partnered with researchers from the University of California in Berkeley, and Tsinghua University in Beijing to apply operations research to develop and implement new software to help CNPC to improve the management of its pipeline network. Previously, all pipeline production and construction planning for CNPC, which controls 72% of the country's natural gas resources and 70% of its pipeline network, was done by traditional methods using spreadsheets. However, due to the increasing size and complexity of the network, the use of the traditional method resulted in excessive costs and wasted resources. Since implementing the new software, which uses a 3-stage convex relaxation method and iterative piecewise linear approximation methods, in late 2014, CNPC has obtained approximately $530 million of American dollars in increased earnings, 2015 to 2017. In addition, the resulting increase in the efficiency of the existing pipeline network allowed the company to postpone the addition of new pipes, leading to an official budget reduction of more than $20 billion of American dollars in construction costs for the following 5 years. The image present the algebraic formulation of the natural gas pipeline transmission model. Without fear of being wrong, it can be said that mathematical optimization models are the goose that lays the golden eggs of China National Petroleum Corporation. High power. Integrated electricity and gas dispatch system. High power integrates the following models. High electricity supply chain optimization supports decisions in the electricity supply chain in terms of sectoral planning and business generation. High smart grids optimization supports the decisions of the various agents involved in the smart grids business. High natural gas supply chain optimization supports the decisions of the actors involved natural gas supply chain at the level of sectoral planning and business generation. The following is the topology of high power. According to the structure of modern electricity markets, the support of the business decision-making power generation should be seen from several points of view. Central agents, formed by the regulator, supervisor, planner, and system operator. Generators, agents that operate power plants. Distributors, utilities enterprises. Traders, smart grids operators, and industrial companies. Hydraulic system physical modeling. High water corresponds to a general model that includes all kinds of hydraulic components, reservoirs, hydroelectric power plants, rivers, overflow channels, connection points and pumping stations, demands, like irrigation, aqueducts, environmental, industrial. Components can be freely linked to form any topology, like pumping storage systems. Hydroelectric power plants are modeled independently of reservoirs, so plant-reservoir connectivity must be established. The regulation capacity of the reservoir is simulated in detail, so such a simulation consistently represents the dispatch of the power plants, considering their ability to regulate the multi-annual, annual, hourly water resource. Electric system physical modeling. Electrical connectivity is carried out through a network of circuits and bars that integrates different types of installations, power plants, like hydroelectric, thermoelectric, coal, wind, solar, biomass, places of demand, like industrial, cities, regional interconnections and energy storages. High power includes the simulation and several types of renewable energy sources and energy storages. For each type of electrical asset, high power includes the exact equations for simulation. Natural gas system physical modeling. High gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are: node, connect the gas system installations; production fields; consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants; transport systems, I, pipelines, and 2, multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. High power, autonomous optimization software for energy sector enterprises. It is an optimization decision support system aimed at agents acting in the energy sector, understood as the union of electricity, natural gas, oil, bio-renewable sources, and new non-conventional sources. For more information, interested parties are invited to watch the video High Power. Use case: Oil Express natural gas field exploitation planning. At the end of the last decade of the last century, Oil Express, a global natural gas company that operated several natural gas producing fields in multiple countries, asked High for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making regarding the exploitation of natural gas field and its impact on Oil Express finances. Solution: design and implementation of a DSS for management of natural gas oil field strategic decisions like the exploitation period. The models included in the DSS were: electricity and gas economic dispatch simulation, optimization of the gas trading decisions, optimization of the financial and fiscal decisions, and financial simulation of the gas buyers. Result: the SHTG model, hydrothermal and gas system, the first version of the actual high power model. Based on the high power, Oil Express makes its decisions that produced successful results that led to higher profits by delaying the exploitation of the gas field for an economically more convenient time, due to the non-sustainability of the market. To stimulate the natural gas market for the electricity sector, government institutions conducted a reference study. This study was taken as a reference to analyze the market using the SHTG model. The main characteristics of the study was: the rolling period was 6 months. 10 plants were considered for take-or-pay contracts with an installed capacity of 2,813 megawatts. The take-or-pay percentage was 30% for the plants of the center and 70% for the plants in the border, and the electricity dispatch planning model used by ISO operator was adapted to represent the impact of TOPS. The model turned out to be correct, since in early 1998 it detected the market crisis between 1998 and 2000, which led to bankruptcies of thermal generation companies. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through TOPS contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. People interested in the case can watch the video. Oil Express, Natural Gas Field Exploitation Planning, using a optimization by sectorial model. The first version of high power, called SHTG, Hydrothermal and Gas Dispatch System, was awarded the Colombian Engineering Award by the Colombian College of Engineers, ASEM, in 1998. SHTG was developed for a global oil company, to jointly analyze the electricity and gas markets. The oil company kindly authorized then decision where, to submit the work, withholding the name and maintaining all confidentiality of the data and results. SHTG was implemented using OpTeX, the optimization expert system. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.